Grab my coffee too.
Okay.
So who's down for faking engagements this weekend for free drinks?
What was that? What was that?
I said, who is down for faking engagements this weekend for free drinks?
So you got a babysitter?
Oh, my kids are with their mom this weekend, so we'll take yours over to her if you want.
I'm good. I think Kurt might take him though.
You know, after today, he probably does need a few drinks.
Well, he's shaved, so he's ready.
I'd have to grab my spine from my wife before we go anywhere.
That was great, man. I like that.
Let's see. La, la, la. Where's my controls? There you are. Why does that happen every time? Not my controls. So stupid. That's like every time I do something, my controls sometimes are over here. Now they're over here. Uh, 10:14. I had 1 minute.
Yeah, you drink that beer. Sorry, guys. I still have some pre-workout in me. I'm very hyper right now.
But at least you're back to normal.
I was hoping to find something ready to go for food, but just had an apple. Small apple at that.
Did Mac give you that apple?
No, I don't accept apples from Mac. Okay, so phone here, I got my pen. Okay. Okay. Is it just me or is it? Let's see.
It's just you.
So we're missing. Christina, you are here, even though. How could you? Isn't it Christina? Christina, don't you live in, are you not there? You're logged in, but you're not really there.
I'm driving right now, but
Yeah.
I zoomed in on my phone.
Of course, you're driving. That makes sense. Okay. All right. Okay. Okay. So chapter 4, guys. I just wanted to kind of start over because we like to review anyway. And so we're going to kind of more or less start over a little bit here. And make sure that I cover everything that's in the book. Magic pen here. Okay. So pulsed ultrasound. But I'm not going to draw the thundercloud again. But remember, it's really important. The reason the pulses occur is because we need one pulse for one echo. Reality is one pulse produces many echoes, but it's one pulse. All those echoes have to come back before the next pulse occurs. If we don't do that, if we send out a pulse and echoes are still coming back and you send out another pulse, total chaos. Cats and dogs living together, sleeping together. With that, when that happens, if a second pulse goes out before all the first echoes come back, now the computer doesn't know what is going on. It doesn't understand that those echoes are still coming back, and it's going to put those echoes in the wrong place on the screen. Our machines are basically depth finders. And if you're messing with the time, and it all has to do with timing, if you mess with the timing, you've messed with the entire screen. It does actually happen sometimes. Engineers have been pretty careful to make sure that it doesn't happen, but it can occasionally happen, and it can produce some interesting results. Okay, so a pulse, just remember, pulse, this particular pulse is made up of 3 cycles. 1, 2, 3. 1, 2, 3. I always draw my single pulses going off in this direction. It just works better for me. It's not. Okay. I always draw my pulses from left to right, and that's just the way, because you read left to right. That's the way I think about it. I can't really think about it any other way. And of course, let's just remind ourselves some things. 1 cycle. I'm kind of drawing it backwards now because it's not so much backwards. I usually do our cycles over here, right? But of course, that is a cycle. This is a cycle. 1 cycle. From here to here is a cycle, and from here to here is a cycle. If I had drawn this a little more accurately, all 4 of these hash marks would be equally spaced. I didn't draw it completely accurately. I made this first part of the pulse a little bit too wide. By making this different widths, what I've really created is 1 frequency up in the front and 1 frequency up in the back. That does not happen like that. It should be 1 frequency from beginning to end of the pulse. So that's just a little bit of inaccuracy I drew into this one. I also draw the beginning of the pulse bigger. In other words, amplitude is higher here than it is here, and then it is here. And that is reality. The pulse quickly is attenuated. stepping forward a little bit in time, we're not talking about this yet. This attenuation is created on purpose by the transducer, by the manufacturers of the transducer. In fact, the fact that this pulse is only 3 cycles long is produced purposely. Remember, if we're going to measure an ant, all right, maybe it's an ant from the, there we go. You want to use a small ruler to measure that ant, or you want to use the yardstick? We don't want to use the yardstick. We want to use the smallest ruler possible. So the analogy there, then, small ruler, small, or short pulse is good or best. Okay. Shorter is better. Looks like I need a little more room here to read this. Oh, I do have my thunderstorm, I forgot. Only pulsed ultrasound can create an image. If you are seeing an image, it has to be pulsed ultrasound. So the analogy I had before, a mild thunderstorm, 1 lightning bolt, 1 sound wave. You see the lightning bolt, you see the light, you count seconds for that sound to get to you, and you've just used the range equation. Continuous wave ultrasound actually does exist, but that kind of ultrasound does not produce a picture. It will produce we could do pulse wave, or I shouldn't say, we can produce a Doppler, but we cannot produce a picture. There will be no picture of a blood vessel with continuous wave. That does not happen. But we can actually get this part, just no picture. And the reason, because it's kind of like a crazy thunderstorm where there's lightning, 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 one right after another. And so many sound waves coming from so many different lightning blasts. You're asking, how far is it? You don't know. Okay, moving forward, this is all review, so I'm kind of going a little quickly here. Pulse duration and spatial pulse length. I decided to put that right in the same spot. Oh, yes, we're recording. Good. I have it on automatic record, which is a bit of a problem sometimes, because when we spend 5 minutes at the beginning of class like we did today, not doing anything, it's all recorded for YouTube. And it already takes an hour and a half, 2 hours for this to upload. And if I go and cut it out, it takes another hour and a half to 2 hours just to cut out 5 minutes at the beginning. It's a real pain. Should be a better system. I'm sure there is, I just don't use it. Anyway, okay, pulse duration. Pulse duration, this is basically like time, right? It's basically similar to period. And in fact, we're going to be adding the period of each cycle in order to find pulse duration. But the pulse duration is from the beginning of the pulse to the end of the pulse. I don't know where I'll go ahead, I'll put my end line here. Because it's 3 complete cycles for that pulse there. Pulse duration, let me just make sure I very simple, but I still have to always check because I don't want to do it wrong. Pulse duration is cycles times period. Yeah, exactly what I was saying. So pulse duration is equal to the number of cycles, in this case 3. It could be more, could be, well, it's probably not going to be less than 3, times the period t in microseconds. Now that period, of course, is going to change with frequency. So different frequencies will create different periods. Higher frequency, smaller period. Typical values of pulse duration, 0.3 to 2.0 microseconds, millionths of a second. Let me just, we'll continue only with pulse duration at this moment. Pulse duration is determined by the sound source. Like I alluded to earlier, when the manufacturers, when the engineers design these, they design a transducer to have the absolute shortest pulse duration possible. In other words, the smallest ruler, because we're looking at very small things. So they purposely, and the way they do that is, yes, through frequency, we change, the frequency changes the period, and that's part of the pulse duration. But when it comes to the manufacturer of the transducer, they're really trying to get as few of these as possible. And I think 3 cycles is probably about as low as you can get, maybe 2 cycles. And we'll talk about how they do that. Is it adjustable? Oh, looks like I have a little. Yes, I said, forgot what I wrote. Is it adjustable? No, it is not adjustable. Okay, so that's pulse duration. Let's just use another color, spatial pulse length. I'm going to put my hash marks here in the same exact spot. Spatial pulse length is equal to the number of cycles. In this case, 3 times wavelength. I'll go ahead. Wavelength lambda, and that's going to be in millimeters. Once again, wavelength is going to be determined by frequency. So obviously, that gotta get out of that mode. Obviously, this frequency and that frequency are going to have different wavelengths. All right. So wavelength, however, remember the speed of sound affects wavelength. Remember that. And that was the one thing that was kind of an aha moment for me a couple of years ago. I never really got the concept. I never really thought about it, I guess. The frequency is the frequency, but the speed will either pull that frequency apart and make it make the wavelength longer, or the speed can the speed can slow down and actually make the wavelength shorter, even though the sound, even though the frequency does not change, the wavelength can change, which is really weird. And that's actually what happens when you breathe in helium. There's a change in the speed of sound. That's all that is. When you start talking like this, the speed of sound has changed. The wavelength, your vocal cords are still vibrating at the same exact rate, because that's what they do in order to create the sound that we think you're going to try to make. But now you're using air with a different speed of sound. That's why it sounds different. Frequency actually has not changed. The wavelength has changed. Okay. Cycles, wavelengths. Okay, so spatial pulse length, cycles times wavelength. Typical values 0.1 to 1.0 millimeters is both sound source and medium. Sound source is the frequency part. The medium is the wavelength part. All right? Frequency is determined by the source. Wavelength is determined by the source and the tissue, or the medium. Adjustable? No. Neither one of these are adjustable. But Kurt says, meh. And I've already explained why it's adjustable. It's just not, it's not adjustable without a pause in the machinery. Oh, and in clinical imaging, a pulse typically contains 2 to 4 cycles. Okay, so they can create 2 cycle pulses. Maybe they could even do 1 cycle pulses, I'm not sure. Okay. So I was gonna just, let's look at, I think I was just going to do this just as a reminder. I had these extra waves down here. I wasn't sure what I was going to do with them. Oh, I know. On both of these, I'm going to put the 1 second mark. Okay, by doing this, I just mixed apples and oranges a little bit. As I did that, I realized. And sometimes my mistakes can help if I catch them. If I don't catch them, then they're not very helpful, are they?
Just add some vodka to it.
Done. No, just kidding. Rum. No, the reason this is apples and oranges is because when I say, when we say, oh, from 0 to 1 second, and that's your frequency, that's continuous wave. That is the fundamental frequency. When I'm talking about pulses, it's not 0 to 1 second. It's actually millionths of a second. So let me just, I'll take away the second. Let's just do this. Z. Okay. Well, in any case, now I'm kind of thinking this isn't going to make as much sense, but if we consider this speed of sound or frequency of this is 1 megahertz of frequency. Even though we're only seeing 3 cycles, that's, remember, 1 tiny little, boop, you pulled out that little pulse. It's still inside of that pulse. It's still, what I say, 1 million. It's still 1 million cycles in a second. It's only just a tiny pulse of 1 million cycles per second. But if we were to make that travel faster in sound, it's still 3 cycles. It's faster in sound. Sound faster in the tissue. The cycles haven't changed. The frequency hasn't changed, but the wavelength has. I'm going to move on. I didn't like that after all. I don't like it. You don't get to hear it. Okay, so now that was mostly a review, right? And I think we just started talking about pulse repetition period before, so let's do that. I'll get you out of the way a bit. Okay. So pulse repetition period and pulse repetition frequency, those are two different sides of the same coin. They are reciprocals, in fact, just like frequency and period. Frequency and period are reciprocals. In other words, perfect. What's the term? Well, perfectly. You know, one over frequency is equal to period. 1 over period is equal to frequency. You multiply them together, they always equal 1. They affect each other perfectly. All right. So pulse repetition frequency and pulse repetition period are reciprocals of each other. I'm going to remind you again, and some of you will be like, I know, and others will be like, I don't know. So I have to remind you again. Pulse repetition frequency is not at all related to the operating frequency. I haven't used this term yet, operating frequency, but I have used frequency. The operating frequency is megahertz, 5 megahertz, let's say. This, and let's just pretend this is a 5 megahertz beam. This is one snippet. That's a good word to use for that, snippet. One tiny little snippet of a greater sound wave of 5 megahertz. So pulse repetition frequency is in the kilohertz range. So not millions of times a second, but thousands of times a second, these pulses are coming out of the transducer. Now, I mentioned the other day that this is that's a false picture. But we have to use it. Just like we have to use, just like this isn't even a true picture of what sound looks like, we have to use it in order to make our measurements. The reason why it's a false picture is because what it's showing is one pulse going in and another pulse following it. That would never, almost never happens in ultrasound. It's one pulse in.
I've seen that question come out a lot in the SPI reviews that I've taken, including the word duty factor.
Duty. Yeah, it's a big deal. It's a big deal to understand that only one pulse at a time with all of its echoes and the next pulse. The amazing part is, guys, is that we're putting in a pulse, we're listening to all the echoes, we're putting in another pulse. And so listening time, by the way, this is listening here. It is like 99% of the time. Think about how fast this sound must be traveling in our bodies. I don't think of sound going this fast, but it is. Well, first of all, it's faster in our bodies considerably faster in our bodies than it is in air, for instance. I'm pointing to the outside, by the way. Thousands of times a second, and it's still listening 99% of the time. So that means it's talking about 1% of the time. That's really amazing if you think about it. It's really something else. Okay. So a pulse repetition period. Your book, you know what, I'll do it the way your book does first, and then I'll do it the way that I do it. Once again, this is just simply the way that I draw my pulse in my pulse direction and everything, and the books always disagree with me on this, but that's okay. From interesting, I think. Oh, no, page 53. I was on the next page. I'm like, that's not right. So it's from the beginning of one pulse to the beginning of the next. The way they draw it, in my personal opinion, they've drawn it from the end of one pulse to the end of the next. So let me draw it the way I prefer. And it really does not matter. The number will be the same. So the beginning of that pulse to the beginning of that pulse. That's just going to drive me crazy. Ugh, it's still driving me crazy. Okay. This whole region is the pulse repetition period. PRP. So that includes one listening time and one pulse. So pulse repetition period then. Just
say that last part again.
The pulse repetition period includes all this listening time. Let's use a different color. So listening time, and then it also includes one pulse duration. So if you just basically you just add those together, you get a pulse repetition period. In other words, period meaning time. Ooh. Pulse repetition period is the time from the start of one pulse to the start of the next pulse. It includes one pulse duration plus one listening time. Units are probably going to be in milliseconds. Typical values, of course, microseconds to milliseconds. So microseconds, or I'm sorry, milliseconds. Microseconds would be the units. Typical values are 100 microseconds. So I guess that's 100 thousandths of a second to, what was the other, 1 millisecond. Oh, I'm sorry. I wrote that wrong. Hold on if you're writing, if you're following along. I'm sorry. And I said it wrong too. So 100 millionths of a second to, what did it say, 1 millisecond, which would be a thousandth. So 100 millionths to 1 thousandths of a second are typical values. It is generally 100 to 1,000 times longer than the pulse duration. So the listening time, no, the overall time. Well, the pulse duration is, in this whole thing, the PRP, remember this is 99% and this is only 1%. So the pulse repetition period is generally 100 to 1,000 times longer than the pulse duration. I'd say probably closer to 1,000 times longer in most imaging. Pulse repetition period is determined by the sound source only. Sound source only. Okay. So wait, was pulse duration? Sound source only. Yes. So you have in the machine something called a pulsar, is a component in the machine that determines how many pulses per second will go out. So that is determined by the source. And like I said, guys, I don't know why, they love, SPI loves testing you on source versus tissue versus both. Not by the medium through which its sound travels. Pulse repetition period is determined by the imaging depth that the sonographer selects. Determined by, is it adjustable? It doesn't say yes or no, does it? I'm just gonna adjustable by depth, and that is, let's be a little more specific. Grayscale imaging. Do Americans, do we spell it with an E or an A? I know the British, I never know which one how to spell it. I can barely spell my own name. So that's all PRP. Actually, no, I'm going to come back up here and stay up here because the pulse repetition, let's see, imaging depth. When the system is imaging at shallow depths, I'll get to that, adjustable. Oh, yes, I'm sorry, I totally missed this on page 53. I was looking at determined by adjustable. Yes, the sonographer changed the pulse repetition period when the adjust the scan's depth of view. So yes, let's just put the word there. Yes, yes, it is adjustable by depth or grayscale. Depth of maximum. Depth of view, transmit time, on time. Okay, so basically I'm just looking through 54, 55 with deeper imaging. Okay. I do want to talk a little bit more about this just to make sure you get it. And I have an extra one of these down here that I could use to talk about. That more at the bottom of my screen. So we have a transducer putting off a sound wave. Excuse me. Thought I used the box. Okay, there's my transducer. It sends off a pulse in this direction. Why? Oh, I got the wrong. Sets off a pulse in this direction. If we limit our depth to here, then all the sound will start bouncing back and eventually make its way back. And let's say at this depth, we're only going 2 centimeters deep. And at 2 centimeters deep, I just know from experience that that takes 26 microseconds for all echoes, all of them return. But if we're going to go farther to this depth, and 3 centimeters, okay, that's not really the scale, but we'll just 3 centimeters depth. Now it's going to take 39 microseconds. I'll tell you the rule on that later, but you can kind of figure out that it's 13. We're dealing in multiples of 13 here. In 39 microseconds, all echoes will return. So let's just get rid of this line here because now we're going a little deeper. So once again, we have sound waves going this way, and then echoes returning, and returning, and returning. You could see it's a farther distance to 3 centimeters. It's 39 microseconds, and so n 39 microseconds. Now all echoes return. So you could see where when you are more shallow, your PRF, your pulse repetition frequency, can go up because it takes less time for us to have to wait for all the echoes to return. If your PRF goes up, then your period is going to go down in the exact same way. Here, I have to slow my pulse repetition frequency down just a little bit. It's only a centimeter difference here. I have to slow it down because I don't want to send out another. If I stick to the PRF here, then I'm going to be sending out sound waves, pulses, before all of these echoes have had a chance to return. So now I have to slow my frequency down, and of course, they're reciprocal. My period has to will go up from there.
Mr. S., I'm sorry to interrupt, but we can barely see what you're writing. It's really light.
Oh, really light? Okay. In any case, so this is my first depth here at 2 centimeters. My second depth here at 3 centimeters. My frequency can be, we want it high, by the way. We want our frequency fairly high because it makes a better frame rate. So this is let's see, very high frequency here. Okay. Do I still sound like Darth?
Yes.
I really hate jumping out and jumping back in. It really messes with the recording too.
Well, we can still hear it too, but it still has a distortion.
All right, let's just hope that things get better here in a second. Okay. I am your father. Anyway, so just to rehash it really quickly, the frequency has to slow down the deeper and the deeper we go has to slow down because we cannot send another pulse out until all echoes are returned. When PRF goes down, PRP will go up. Okay, let me jump back to where we were. Duty. Oh, all right, now I've created a mess. I'm going to have to get rid of this too. Let me go through here. I've told you everything, but I just right off the bat I saw a couple of terminologies that I didn't use yet. So I told you as depth of view increases, the pulse repetition period increases. You have to wait longer. But on 54, the two components of the pulse repetition period are transmit time or on time and receive time. Let's just write those words in. That would basically be pulse. Whoops. PRF, pulse repetition frequency, is the number of pulses that an ultrasound system transmit into the body each second. With regard to PRF, the number of cycles in each pulse is meaningless. We are interested only in the number of pulses. So the cycles mean nothing. It's simply how many of the pulses are in each one. They're typically in hertz or kilohertz. Typical value is 1,000 to 10,000, so pretty much they're all kilohertz. 1,000 to 10,000 hertz, or 1 to 10 kilohertz. Pulse repetition is determined by the sound source, not by medium. And once again, when we change the depth, when we change our depth button, we're changing the pulse repetition frequency, and therefore these two are, you can't separate them. Are inversely related. Well, they're not only inversely related, but they are reciprocals. As depth of view, adjust the depth. Okay, I pretty much already. Let's just do this. And real simple, PRF is equal to 1 over PRP. In other words, reciprocals. Anytime you multiply a reciprocal together, PRF times PRP is going to be equal to 1. That relationship is just special. It's a special kind of inverse relationship, reciprocal. These two will always equal 1. Like I said, you cannot separate PRP and PRF. They're hits. Let's see. Time. 11 o'clock. Okay, we're good. Duty factor. The percentage or fraction of time that a system transmits a pulse. So we've danced around this already. The duty factor. We've already talked about talk time or transmit time or the pulse duration. All of those are all saying the same thing. And then we've also talked about the listening time in between pulses is our listening time. So we've kind of danced around this already. There are no units. It's a percentage only. Actually, it could be written as a ratio or a percentage. But in either case, no units, no time units, no length measurements or anything like that. In clinical imaging, duty factor ranges from, so as a ratio, 0.002. Let's put 0.002 and 0.005. Or another way of saying that is 0.2 to 0.5%. You know what? I think I said it, but I didn't really write it. Duty factor. When we say 0.2 to 0.5%, that is percentage of time unit is it's transmit. I'm just going to say talking. Percentage of time the unit is talking, or the percentage of time the unit is transmitting, or the percentage of time the unit is, why can't I think of, on, pulsing, transmitting, talking. It's really all the same thing. In other words, it's what percentage is it doing this rather than that. When creating anatomic images, duty factors are in the range of 0.2%, indicating that ultrasound systems spend a very small time transmitting and very large percentage of time receiving. So I said 99%, really 99.8% listening time. Duty factor is determined by the sound source only. It is adjustable with depth because, like I said, we skirted around this already. It's really the same thing. We're looking at, up here, we were looking at PRP and PRF, the pulse duration versus the listening time. This is really very close to the same thing. Up there, we're talking about the frequencies or the time. Duty factor is just simply looking at percentage. it's really the same thing as that we already talked about. Duty factor is inversely related to imaging depth. Okay, so inversely related to depth. Well, we've kind of talked about that already as well. If you think about it, typical imaging listening time is 99.8 and transmit time is 0.2%. But it's going to change a little bit. The deeper you go, the less time transmitting and the more time listening. The more time it takes for all those echoes to come back. So the deeper equals a longer, I'm just going to say wait. A longer wait, a longer listening time. Longer wait is the same thing as saying less time same as less time. Dang it, I do that every time. Dang. More about duty factor. How is duty factor calculated? Oh, fun. I forgot we do have to do this too. Let's at least give us a pretty color, huh? So, duty factor. Remember, we could figure this out just like this without a percentage. Or we can figure it out with a percentage. It's just one more step. We'll put the percentage point in there, or the percentage sign in there for now. Pulse duration divided by pulse repetition, period. In order to make it a percentage, we just simply multiply by 100. That's why either 0.002 or 0.2%. Oh, what are the maximum and minimum values for duty factor? The maximum value duty factor is 1 or 100%. Ah. So we've been saying that duty factors are, typical duty factors are 0.2 to 0.5, not even a percentage of time talking, unlike me, right? But much more time listening. But we do have ultrasounds that have, let's see, 100% exists. It does actually exist. Know what I'm looking for here? Dang it. Not at all frustrating. %, or duty factor of 1 or 100% that do exist. Continuous wave transducers. They do. There is a thing. We just don't. We don't use them. In fact, I have actually used continuous waves, but so general ultrasound technologists typically don't use continuous wave transducers, but Ecotechs do. The Hart guys, they do. So let's see. Continuous wave sound cannot create anatomic images. We talked about that. Minimum duty factor is 0. Okay, so once again, this is adjustable with depth. Well, that makes sense because this is really just an extension of PRF, PRP, and that was adjustable with depth, at least in grayscale. So I have my depth of view. The minimum duty factor is 0. That doesn't make sense. That just means the machine's turned off. There's no such thing as. There couldn't. Obviously 0. If you don't put any pulses out, then you're not going to get much imaging. It'd be kind of a boring day. Okay. Duty factor. I'll just mention that. I think. I actually have chapter 5. It's an easy chapter. Easy, but it's new concepts, so I'm not going to touch 5 right now. So duty factor is also related to bioeffects. So how many pulses a second go into your body affects how much heat is created in your body. Like I said, for adults, that's just it's not even an issue unless don't ever put the transducer on your eyeball because that's probably one spot that you can possibly cause some damage. But for a shallow imaging, so the shallower we go, the faster the pulses go because less time waiting. So you don't have to wait. It's shallow. You don't have to wait very long. Pulses, pulse, 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 pulse. And you go deeper. It's pulse, pulse, and you go deeper still. Pulse, pulse. And so that deeper imaging has a less duty factor, a lower duty factor. Shallow imaging has a high duty factor. So if you ever do scan your eyeball, you have a high duty factor, you have lots of pulses, 10,000, 12,000 pulses per second. Not to mention, these machines they're set up for a little higher strength than is what is required for the eyeball. So I say that because I did it once. It's kind of cool. No, I can't see on this side. Let's see. It is 11:14. Awesome. You know what? This is enough for today anyway. What I was going to do is do a full day and then review the test after hours, but I think we can get the review done within our regular allotted time, so that works. This works out fine. So, but I am going to stop recording. Don't need you guys start recording.